When people talk about green hydrogen, they often speak as if it were a product you could simply buy, install, and switch on. As if hydrogen were a machine you could deploy the way you deploy a solar panel or a battery. But this way of thinking is precisely why so many hydrogen conversations feel confusing, contradictory, or disconnected from reality. Green hydrogen is not a product. It is not a device. It is not even a single technology. It is an industrial value chain that behaves more like an ecosystem than a gadget. A useful way to understand this is to imagine explaining the oil industry by pointing only to a gasoline pump. You could talk about nozzle design, flow rate, or octane ratings, but none of that would explain why oil reshaped geopolitics, infrastructure, and global trade. The gasoline pump makes sense only because an entire upstream and midstream system already exists behind it. Exploration, production, pipelines, refineries, storage, shipping, and regulation. Hydrogen is at the same stage of misunderstanding today. We keep pointing at one visible piece and expecting it to explain the whole system. This misunderstanding creates unrealistic expectations. When hydrogen projects succeed, they are praised as technological breakthroughs. When they fail, hydrogen itself is declared flawed. But in reality, success and failure are not driven by the chemistry of hydrogen. They are driven by whether the entire chain around that chemistry has been designed coherently. Hydrogen behaves less like a technology and more like a logistical organism. If one organ fails, the whole body suffers. Another way to approach this is to think in terms of coordination, not innovation. Most of the components required for green hydrogen already exist. Electrolyzers are not new, compression is not new, storage is not new, fuel cells are not new. What is new and difficult is coordinating these components across time, geography, regulation, and economics. Hydrogen is not waiting for a breakthrough, it is waiting for alignment. This is why so many hydrogen discussions feel strangely detached from operational reality. We talk about cost targets without talking about utilization. We talk about capacity without talking about throughput. We talk about emissions without talking about infrastructure load factors. These gaps exist because people are trying to reason about a value chain as if it were a single widget. But value chains do not optimize locally, they optimize system-wide. To see this clearly, consider a simple thought experiment. Imagine a hypothetical electrolyzer that is perfectly efficient, costs nothing, never degrades, and lasts forever. In most hydrogen narratives, that would solve the problem, but in reality, it would not. You would still need electricity at scale, you would still need water treatment, you would still need compression, storage, transport, and customers. You would still need permits, safety systems, and financing. The hydrogen value chain would still exist, unchanged. The electrolyzer was never the system. This is why focusing on single variables, electrolyzer cost, efficiency, or scale, consistently leads to disappointment. Improvements in one link often expose constraints in another. Lower production costs increase the importance of storage. Higher output increases transport bottlenecks. Cheaper hydrogen increases demand for infrastructure that may not exist yet. This is not a flaw. It is how value chains behave. Another creative way to think about hydrogen is as delayed energy. Unlike electricity, which is consumed almost instantly after generation, hydrogen stores energy in molecular form and releases it later, elsewhere. This delay introduces optionality, but it also introduces risk. Every delay requires custody, handling, and conversion. Each step has losses. Hydrogen is not inefficient by accident. It is inefficient by design because it trades efficiency for flexibility. Understanding hydrogen means understanding when flexibility is worth paying for. This is why hydrogen often works in places where time, not energy, is the limiting factor. In warehouses, downtime is expensive. In industrial processes, interruptions are costly. In backup power systems, failure is unacceptable. Hydrogen does not win because it is cheap. It wins because it reduces certain types of risk that other technologies cannot. That is a value chain benefit, not a technology feature. Conversely, hydrogen struggles where immediacy and simplicity dominate. If electricity can flow directly from generation to use with minimal friction, adding hydrogen in between almost always makes things worse. It adds steps, costs, and points of failure. This is not because hydrogen is bad, it is because the value chain is unnecessary in those contexts. A chain that does not add value becomes a liability. This framing also explains why hydrogen adoption looks uneven and fragmented. It is not spreading evenly across sectors because value chains do not spread evenly. They emerge where all links can be satisfied simultaneously. That is rare. Most regions can satisfy some links but not others. A place might have cheap power but no water, or strong industrial demand but no grid access, or good logistics but poor permitting. Hydrogen requires coincidence, not just capability. This is why hydrogen hubs are such a dominant concept. They are not about scale for its own sake. They are about synchronizing the value chain spatially. When production, storage, transport, and use are co-located, the chain shortens. Losses decrease, utilization improves, risk concentrates but becomes manageable. This is not unique to hydrogen. It is how every heavy industrial value chain has matured historically. Understanding hydrogen as a value chain also changes how we think about companies in the space. Firms that focus on one link often struggle to capture value unless the rest of the chain is already in place. Firms that integrate multiple links, even imperfectly, often perform better because they control interfaces. This is why ecosystem-oriented companies tend to outperform component sellers in early-stage industrial transitions. Integration compensates for immaturity. This dynamic is visible in how companies like Plug Power approach the market. Rather than waiting for a perfect hydrogen economy to emerge, Plug Power built controlled, closed-loop systems where production, storage, and consumption were aligned. The success was not technological brilliance, it was value chain containment. Control beats optimization when systems are young. On the industrial side, companies like Air Liquide demonstrate the opposite but equally important lesson. Hydrogen becomes manageable when it is treated as an industrial gas, not a futuristic fuel. Standardization, redundancy, long-term contracts, and conservative engineering matter more than novelty. This mindset accepts that hydrogen is infrastructure, not disruption. Electrolyzer manufacturers like Nel ASA sit at an interesting junction in the value chain. They are often portrayed as the drivers of hydrogen adoption, but in reality they are responders to system readiness. Demand for electrolyzers rises when power, policy, and offtake align. It falls when they do not. Electrolyzers follow systems, they do not create them. Another overlooked aspect of hydrogen as a value chain is time mismatch. Most hydrogen discussions assume synchronous development, production, infrastructure, and demand rising together. In reality, they rarely do. Infrastructure often leads demand or lags it. Policy often precedes economics. Capital often waits for certainty. These mismatches create periods where hydrogen appears to fail, when in fact it is simply misaligned in time. This temporal misalignment is one reason financial modeling plays such a central role in hydrogen. Models are not just about cost, they are about timing. They test whether capital deployment, utilization ramp-up, and revenue realization align closely enough to survive. A hydrogen project can be technically sound and still fail because cash flows arrive too late. That is a value chain timing failure, not a technology failure. Viewing hydrogen as a value chain also reframes sustainability. Sustainability is not achieved by labeling hydrogen green. It is achieved by managing the entire chain responsibly. Clean power sourcing, water stewardship, material durability, infrastructure utilization, and life cycle emissions all interact. A green input does not guarantee a green outcome if the chain around it is inefficient or underused. This is why the question, is hydrogen sustainable, is poorly formed. The better question is, which hydrogen systems are sustainable under which conditions? Sustainability is contextual. It emerges from design choices, not labels. Treating hydrogen as a monolithic solution obscures this reality. Ultimately, the reason green hydrogen is so often misunderstood is because value chains are harder to reason about than technologies. They require thinking across disciplines: engineering, economics, logistics, policy, and human behavior. They resist simple narratives, they punish shortcuts, but they also reward coherence. Green hydrogen will not reshape the energy system because one component becomes cheap enough. It will matter where entire systems are designed to make it matter. It will appear boring where it works and controversial where it doesn't. That is the hallmark of infrastructure, not hype. This is the lens ReneEnergy brings to the conversation. We do not ask whether hydrogen is good or bad. We ask whether a given hydrogen system makes sense, technically, economically, and operationally. Green hydrogen is not a single technology waiting to be perfected. It is a full industrial value chain waiting to be understood.